Heidi-ho, Renaissanceteers, and welcome to the solution of Renaissance problem number 92. Take it with a grain of salt. Renaissance problem 92 posed two challenges. First, compute the mass and weight of a grain of salt, and second, calculate the force of gravitational attraction between two solid balls of lead, the same diameter as a basketball. Here is all the information you need to do the calculations of this problem. If you would like to do the problem before seeing the answer, now would be the time to stop watching this video. I'll give you a moment to turn it off. Oh, I know a little song, it isn't very long, a deedle-um, a deedle-dee, and now it's all gone. Okay, if you're still here, it means you want to see the solution, so let's begin. The density of salt is given in grams per cubic centimeter. So let's calculate the volume of the grain of salt in cubic centimeters. The grain is a cube, 0.4 millimeters on each side, and a millimeter is a tenth of a centimeter. So 0.4 millimeters is equal to 0.04 centimeters. The volume of a 0.04 centimeter cube is 0.04 centimeters cubed, which is 0.000064 cubic centimeters. Now mass is equal to volume times density, so the mass of our grain is 0.000064 cubic centimeters times 2.17 grams per cubic centimeter, which is 0.000139 grams. The gravitational constant g is given in meter kilogram second units, so let's convert the mass of the salt grain to kilograms. To convert grams to kilograms, divide by 1,000. So 0.000139 grams is equal to 0.000000139 kilograms. Keeping track of all those zeros is a bother, so let's use scientific notation. So here we have 0.000000139 kilograms, which is equal to 1.39 times 10 to the minus 7th kilograms. Or alternatively, you can write it in this form. It's equal to 1.39 times 10 with an exponent of minus 7. Now let's calculate the weight of the grain of salt in newtons. We live on the surface of the Earth, so when we talk about the weight of an object, we mean Earth's force of gravitational attraction on that object. Unless you happen to live on the International Space Station, where everything weighs zero. Weight is the force of gravity on an object on the surface of the Earth. Newton's law of gravity says that the gravitational force between two masses is big G times the product of the masses divided by the distance between them squared. So we have big G, the gravitational constant, in units of meters cubed divided by kilograms second squared. M1 is the mass of the Earth in kilograms. M2 is the mass of the grain of salt, also in kilograms. We want to be consistent with our units. And R is the radius of the Earth, which is 6,378 kilometers, or 6.38 times 10 to the 6th meters. We are standing on the surface of the Earth, but don't make the mistake of thinking that the distance between us and Earth's mass is 0 meters. Newton showed that a symmetrically spherical mass behaves as if it is all concentrated at a point in its center. So for us and our grain of salt, the R in the equation is the radius of the Earth. So the weight of the grain of salt is calculated as big G times the mass of the Earth times the mass of the grain of salt divided by their distance squared, which works out to be 1.36 times 10 to the minus 6 kilograms meters per second squared, which is 1.36 times 10 to the minus 6 newtons. So a million grains of salt would weigh about 1.36 newtons, which is about the weight of a quarter pounder. Now let's figure out the mass of the 24 centimeter diameter lead ball. The volume of a sphere is 4/3 pi r cubed, where r is the radius of the sphere and pi is approximately 3.14. The radius is 1/2 the diameter, so r is equal to 1/2 of 24 centimeters, which is 12 centimeters. Thus the volume of the lead sphere is 4/3 pi times 12 centimeters cubed, which is equal to 7,238 cubic centimeters. Mass is equal to volume times density. Thus the mass of the lead sphere is 7,238 cubic centimeters times 11.34 grams per cubic centimeter, which is equal to 82,079 grams, or approximately 82 kilograms. A kilogram weighs about 2.2 pounds, so 82 kilograms weighs about 180 pounds, which just so happens to be the mass of the Red Sox rookie star Brock Holt. So the mass of Brock Holt is equal to the mass of a solid lead basketball. It's always nice to have these visual references. Now let's calculate the gravitational attraction between two solid lead basketballs in contact with each other. Again, we use Newton's law of gravity. The distance between centers is 24 centimeters, which is equal to 0.24 meters. So we have force is equal to big G times the mass of ball 1 times the mass of ball 2, both 82 kilograms, divided by the distance between them squared, which is 0.24 meters squared. This equals 7.79 times 10 to the minus 6 newtons. Let's compare this force to the weight of a grain of salt. We have the ratio of 7.79 that we just calculated to 1.36, which is the calculation of the weight of a grain of salt earlier. And this is equal to approximately 5.7. So the force of attraction between the two solid lead basketballs is a little less than the weight of 6 grains of salt. How did Henry Cavendish measure such a small force with the instrumentation available back in 1797? The Cavendish experiment of 1797. Henry Cavendish used an instrument invented by Charles Augustin de Coulomb called a torsion balance. Coulomb used it to measure the attraction between electrical charges. A torsion balance has a spring like the one found in rotating ball clocks. You can see a video of a rotating ball clock at this link. The rotating ball assembly is hanging by a thin fiber, and it takes very little force to twist the fiber. Cavendish used smaller weights than the solid lead basketballs of our exercise, so he was measuring a force even smaller than a single grain of salt. Think about how difficult it must have been to make that measurement accurately. If you walked near the balance, just the gravity of your body would throw the measurement far off. So Cavendish used a telescope to make the measurement from a distance, and he enclosed the balance in a box to prevent small air currents from disturbing it. Read about it here. It's a fascinating story. I hope you enjoyed this presentation, and happy Renaissancing.